Okay, hi everyone. We're gonna start delving into Xv6 operating system interfaces. The job of an operating system is to share a computer among multiple programs and to provide a more useful set of services than the hardware alone supports. An operating system manages and abstracts the low-level hardware so that, for example, a word processor need not concern itself with which type of disk hardware is being used. An operating system shares the hardware among multiple programs so that they run at the same time. Finally, operating systems provide controlled ways for programs to interact so that they can share data or work together. An operating system provides services to user programs through an interface. Designing a good interface turns out to be difficult. On the one hand, we would like the interface to be simple and narrow because that makes it easier to get the implementation right. On the other hand, we may be tempted to offer many sophisticated features to applications. The trick in resolving this tension is to design interfaces that rely on a few mechanisms that can be combined to provide much generality. This book uses a single operating system as a concrete example to illustrate operating system concepts. That operating system, Xv6, provides the basic interfaces introduced by Ken Thompson and Dennis Rich's Unix operating system, as well as mimicking Unix's internal design. Unix provides a narrow interface whose mechanisms combine well, offering a surprising degree of generality. This interface has been so successful that modern operating systems, BSD, Linux, macOS, Solaris, and even, to a lesser extent, Microsoft Windows, have Unix-like interfaces. Understanding Xv6 is a good start toward understanding any of these systems and many others. And Figure 1.1 shows Xv6 takes the traditional form of a kernel, a special program that provides services to running programs. Each running program called process has memory containing instructions, data, and a stack. The instructions implement the program's computation. The data are variables on which the computation acts. The stack organizes the program's procedure calls. A given computer typically has many processes, but only a single kernel. When a process needs to invoke a kernel service, it invokes a system call, one of the calls in the operating system interface. The system call enters the kernel performs a service and returns. Thus, a process alternates between executing in user space and kernel space. As described in detail in subsequent chapters, the kernel uses the hardware protection mechanisms provided by a CPU to ensure that each process executing in user space can access only in its own memory. The kernel executes with the hardware privileges required to implement these protections. User programs execute without those privileges. When a user program invokes a system call, the hardware raises the privilege level and starts executing a prearranged function in the kernel. The collection of a system calls that a kernel provides is the interface that user programs see. The Xv6 kernel provides a subset of services and system calls the Unix kernels traditionally offer. Figure 1.2 lists all of Xv6's system calls. Okay, so kernel and two user processes. There's a user space and the kernel space. And with the system call, we could get access to kernel to do something important that has access to hardware. Okay, let's take a look at 1.2. PID equal fork, printf, parent child, PID, printf s, printf exit, fork error. This is a bigger 1.2? Oh, that's it right here. Okay. Fork, exit, wait, kill, get PID, pause, exec, spark, open, write, read, close, dub, pipe, stitch dir, make dir, make not, fstat, link, unlink. That's it. Oh, pretty lean. I love it. The rest of this chapter outlines Xv6's services, processes, memory, file descriptors, pipes in a file system, and illustrates them with code snippets and discussions of how the shell, Unix's command line user interface, uses them. The shell's use of system calls illustrates how carefully they have been designed. The shell is an ordinary program that reads commands from the user and executes them. The fact that the shell is a user program and not part of the kernel illustrates the power of the system call interface. There's nothing special about the shell. It also means that the shell is easy to replace. As a result, modern Unix systems have a variety of shells to choose from, each with its own user interface and scripting features. The Xv6 shell is a simple implementation of the essence of the Unix born shell. The implementation of the Xv6 shell can be found at 7850. The link is a hyperlink to the relevant Xv6 source code, MIT PTOS, and the specific number referred to the sheet and line number in Xv6 source booklet PDF, as in the Leon's commentary on Unix 6th edition. A good practice is to try to read the source code first on your own, your favorite development environment on GitHub or in a PDF viewer, and then come back to this book. By the end of this book, you should be able to understand every line of Xv6 source code without having to consult this book. Okay, so they recommend us to read this code. Let's do that. All right. Copy link address. What? Something's loading really bad. Okay, Chromium. Okay. There's a kernel, MKFS, user. You need a risk-free ulib toolchain from GNU toolchain and Camo. Okay. Autoconf automake. Okay, so the installations that's required to install the toolchain. All right. Interesting. Okay. Let's go back to the article. Processes and memory. An Xv6 process consists of user space memory and per process state private to the kernel. Xv6 time shares processes. It transparently switches the available CPUs among the set of processes waiting to execute. When a process is not executing, Xv6 saves the process's CPU registers, restoring them when it next runs the process. The kernel associates process identifier, or PID, with each process. A process may create a new process using the fork system call. Fork gives a new process an exact copy of the calling process's memory. Fork copies the instructions, data, and a stack of the calling process into the new process's memory. Fork returns in both the original and new processes. In the original process, fork returns the new process's PID. In the new process, fork returns 0. The original and new processes are often called a parent and child. For example, consider the following program fragment written in the C programming language. The exit system call causes the calling process to stop executing and to release resources such as memory and open files. Exit takes an integer status argument, conventionally 0 to indicate success and 1 to indicate failure. The wait system call returns the PID of an exited child of the current process and copies the exit status of the child to the address past the wait. If none of the caller's children has exited, Wait waits for 1 to do so. If the caller has no children, wait immediately returns -1. If the parent doesn't care about the exit status of a child, it can pass a 0 address to wait. In the example, the output lines parent child equal 1, 2, 3, 4, child is exiting might come out in either order, depending on whether the parent or child gets to its printf call first. After the child exits, the parent's wait returns, causing the parent to print. Although the child starts with a copy of the parent's memory, the parent and child execute with separate memory and separate registers. Changing a variable in one does not affect the other. For example, when the return value of wait is stored into PID in the parent process, it doesn't change the variable PID in the child. The value of PID in the child will still be 0. The exec system call replaces the calling process's memory with a new memory image loaded from a file stored in the file system. The file must have a particular format, which specifies which part of the file holds instructions, which part is data, and which instructions to start. Xv6 uses ELF format, which Chapter 3 discusses in more detail. Usually the file is the result of compiling a program source code. When exec succeeds, it does not return to the calling program. Instead, the instructions loaded from the file start executing at the entry point declared in the ELF header. Exec takes 2 arguments, the name of the file containing the executable, and an array of string arguments. For example, echo, hello, 0. This fragment replaces the calling program with an instance of the program running with the argument list echo hello. Most programs ignore the first element of the argument array, which is conventionally the name of the program. The Xv6 shell uses the above calls to run programs on behalf of users. The main structure of the shell is simple. CMain, the main loop reads a line of input from the user to get a CMD. Then it calls fork, which creates a copy of the shell process. The parent calls wait while the child runs the command. For example, if the user had typed echo hello to the shell, run CMD would have been called with the echo hello as the argument. Run CMD runs the actual command. For echo hello, it will call exec 7927. If exec succeeds, then the child will execute instructions from echo instead of run CMD. At some point, echo will call exit, which will cause the parent to return from the wait in main 8001. Okay. So it started the chapter with a for command, and then introduces this new concept where um, the system call echo, um, and how it is being called, how is it compiled and then being run on a day-to-day basis. Say if you type the terminal echo hello, then this is the thing that runs in the background to see the hello on the output. So let's see how it's written in. Copy link address. Go to that int main void. Oh, this is a very weird way of writing program. You have an int and then the line below there's a main, and the indent is 2. Holy moly. Okay. File description. Open console. Okay. Okay. You get a command in the buffer, and then You read it, get CMD. Okay. Um, then, oh, just in case there's a trailing white space. Um, Continue. Mhm. Command is C. Command 1 is D. Fork 1. Mhm. Run CMD. Okay. So whatever the command this passes, the run command is executed. Um, this file is a run command, parse command. Okay. So not that interesting. Just a fork with the command. All right. Mm-hmm. Called exact. Mm-hmm. Okay. So my question here is then, what does the exact here is actual function that get executed or something we defined? Um, so to run in the echo hello, for example, this exact function needs to be parsed as well. I have no idea. You might wonder why fork and exec are not combined in a single call. We'll see later that the shell exploits the separation in its implementation of I/O redirection to avoid the wastefulness of creating a duplicate process, then immediately replacing it. Operating kernels optimize the implementation of fork for this use case by using virtual memory techniques such as copy on write. Xv6 allocates most user space memory implicitly. Fork allocates the memory required for the child's copy of the parent memory. The exec allocates enough memory to hold the executable file. A process that needs more memory at runtime can call sbrk to grow its data memory by n0 bytes. A file descriptor is a small integer representing a kernel-managed object that a process may read from or write to. A process may obtain a file descriptor by opening a file, directory, or device, or by creating a pipe, or by duplicating an existing descriptor. For simplicity, we'll often refer to the object file the descriptor refers to as a file. The file descriptor interface abstracts away the differences between files, pipes, and devices, making them all look like streams of bytes. We'll refer to input and output as I/O. Internally, the Xv6 kernel uses the file descriptor as an index into a per process table, so that every process has a private space of file descriptors starting at 0. By convention, a process reads from. Okay. Hmm. So I think rather than reading this whole book, I think we need to just dig in to find out what kind of steps we should set up to be able to run this program, and then try the exercise instead of getting the introduction on everything. So let's skip this part and dive right into the operating system itself.